All right, welcome back. So today we are continuing this lecture on numerical integration of ODEs. Specifically, we're trying to predict a trajectory of a nonlinear system x dot equals f of x. And when I say a trajectory, I literally mean I want to know kind of where x goes in time. So if I have some initial condition x naught, I want to be able to step this forward at discrete delta t's in time. So I want to be able to get x at time step 1, x at time step 2, x at time step 3, dot, 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 all the way up to some nth time step. These are vector states, so each of these x's might be a whole set. It's the minimal vector describing my system. So for example, later I'm actually going to code this up. We're going to look at the mass on a spring with a damper, and the minimal state to describe this system would be x, this vector state, equals its position and its velocity. So I hope you're okay at this point. This has been many, many lectures where we write down our vector state with an underbar, and that's the vector of positions, the vector of states needed to minimally describe our system. And in this case, for F equals ma physics systems, the position and its first derivative, the velocity, is kind of a minimal state needed to describe that system as a first order system of differential equations. So that's what I mean by this. These are all kind of vector states evolving in time. And so specifically, when I say subscript here, that means at the third time step, or at the second time step, or at the first time step. So x at the kth time step is x at time tk, where tk is being sampled uniformly in time at delta t intervals. So imagine you have kind of some metronome measuring every delta t. And so the tk, the kth time instant, is just k times some delta t. And generally, we're going to choose delta t to be a small time step used to sample our system and to numerically step our system forward. So the name of the game here is to build a numerical scheme, this numerical integrator, that will approximate the system, how to move the system forward in time. So specifically, if I have x at time k, how do I step that forward to x at time k plus 1? There's going to be some big function f that we're going to derive today that if I have x at time k, it'll map my system forward to the next time step, k plus 1. Okay? And if I have that function f, then I can start with my initial condition x naught, and I can map that to x1 with f. I can map that to x at the next time step 2 with f, and I can keep doing that to build this trajectory all the way up to some x at time step n. And so the way we're going to do that, so I'm going to start off really, really simple. In this video, what we're going to do is we are going to start by deriving the simplest numerical integrator, the simplest function f that steps our system forward, based on a finite difference derivative approximation to x dot, to dx dt. This is the forward and backward Euler integration schemes. So today I'm going to be talking about Euler integration, which is really the simplest scheme possible. And we are going to code up an example, and then in the next lectures, I'm going to tell you how to analyze these numerical integrators for their error properties and stability properties. Okay, so let's get started. The basic idea here is that we're going to take our x dot equals f of x, and we are going to replace this perfect analytical derivative dx dt. We're going to replace dx dt with our approximation of the derivative, which is, so if x is a function of time, then dx dt is also a function of time. The derivative of my state x is also a function of time. So really, I've been a little sloppy. This is really x dot of time equals f of x, which is also a function of time. At some time instant t, the derivative of x with respect to t equals f evaluated at my state at that time instant t. And so I can write this as dx of t dt equals, or it's approximately equal to x at t plus delta t minus x at t divided by delta t. Okay, that's a very valid approximation. And we saw earlier, of course, from calculus, if we take the limit as delta t goes to 0, then this is exactly the derivative x dot. But numerically in a computer, we're not going to take this limit as delta t goes to 0. We're going to pick a finite but small delta t to approximate this derivative. And that, of course, because it approximates x dot, it also approximates f of x. So this also approximates f of x at time step t. Okay? And so now for any time step, for any time t, now what I can do is I can multiply both sides by delta t and add x of t, and I get this nice expression that x at time t plus delta t equals x of t, my current time, plus delta t times f x of t. Really, really simple update rule that if I have my state x at time now, at time t, I can evaluate this, and I can get my state x at my next time step t plus delta t. And again, these are all vector x's with underbars. If I haven't, written them down, please forgive me. Sometimes I forget to make sure these are all vector x's, my state of my system. They might be a 2-dimensional vector, they might be a million-dimensional vector, but x is, a state of my system. And this is an update rule. So this is literally this f I'm talking about. This is some big F of x of t. And so in particular, if I have x at tk, and I apply this function to it, that will give me x at time tk plus 1. Okay, so let's just, I think this is pretty easy to verify that this is true. X at time tk plus 1 is x at k plus 1 delta t. So that's k plus 1 delta t, which of course equals x at k delta t plus delta t. Okay, that's just expanding this time here, which equals x at, this is tk plus delta t. Okay, I'm just showing you kind of how you can very, very naturally go from an index, tk plus 1 literally means k plus 1 delta t's, which is the same as tk plus 1 delta t. These are equivalent. Okay, that's all the stuff on the left. And that equals my big f function, this function here, evaluated at time t, tk. So that equals x at time tk plus delta t f of x at time tk. Okay, good. So what I've shown you is that x at time tk plus 1 is this f of x at time tk. That is literally like if I have x at time now, I can step that forward to 1 delta t in the future. And so this is kind of the scheme. I could also write this with subscripts. I could say xk plus 1, because that's x at time tk plus 1, equals x at time k plus delta t f of x at time k. And this is usually the form I'm actually going to write it. So I went through all of this kind of indexing, and I hope I didn't lose anyone. But I did that specifically to show you that this finite difference derivative, where I was thinking of x as a continuous function of time, we can then, if we pick discrete time updates, discrete delta t time steps, we can go through all of this math and write this down using this index notation. And the way I read this, I like to say this in words: x at time step k plus 1 equals, or it's approximately equal to x at my current time step tk plus a little delta t times my function f evaluated at x at my current time step k. So every time you see x sub k, that means x evaluated at t sub k, my kth time step, which is k delta t. Okay, good. So that's the notation we're going to use for all of these lectures. And this is my forward Euler scheme. So this is forward Euler. Forward Euler. And we'll find out that this is an okay approximation scheme for my trajectory, but it's not very good. It's like the simplest thing you can do. Just like this is not a very good approximation of the derivative, there's way better approximations of the derivative. This is kind of, the first, quickest, dirtiest numerical integrator you could write down is forward Euler. But it works in a pinch, and it's really easy to analyze. So that's where we're going to start. Okay, good. What else do I want to show you? So I'm going to show you how to do something called backward Euler, and then we're going to code this up on the spring mass system, and we're going to analyze a little bit of what these mean. Maybe I'll give you a picture real quick of how to interpret this. So again, let's say I have some vector field like the Gulf of Mexico vector field from before. Okay, so this is some vector field where my particle x lives inside this vector field, and it's moving around in x dot equals f of x. Let's for now assume that this vector field doesn't change, so it's a really still day, and it's not changing. It's just kind of a constant flow velocity. And what we're trying to do is we are trying to take, we have, let's say, x at time step k, and we're trying to step it forward to x at time step k plus 1. Okay, and so what we do with forward Euler, this is a really simple interpretation of forward Euler. The way that you integrate forward in time is you query your system. You say, what is my vector field? What does my vector look like at my current location x at time step k? So x now, maybe I have a vector that looks like this. Okay, that is like dx dt. That's my dx dt vector, how much x changes in t. And since we're time stepping delta t forward in time, I want to know how much my system goes forward in time. I literally take that vector v times a little delta t, and I add it to my current xk. That's kind of, morally what's happening here. As I take this vector, which is f of x at time k, I multiply it by a little delta t because I'm taking a delta t time step. And this is, my derivative of x with respect to time, and this is how much time I'm going. So I take a little, v times delta t step, and that gives me xk plus 1. It's that simple. Forward Euler is that simple. At my current time step, it's my current time step plus this little delta t times my velocity step, and that's xk plus 1. And then at xk plus 1, I query my vector field, and maybe now at xk plus 1, it's pointing in this direction. And so now I take a little delta t step in that direction to get xk plus 2. And now maybe at xk plus 2, my vector is pointing in this direction. And so I take a little delta t step in that direction, and that gives me xk plus 3. And so you can see it's almost this little piecewise linear approximation. And I'll show you in a minute. It's based on a kind of first order Taylor series approximation of this derivative, okay, as you might expect, because this is a first forward difference derivative. I'm only using kind of the first term of the Taylor series approximation to get this. I'll come back to that in the error analysis. But this is a picture that shows you kind of morally what this forward Euler scheme is doing, okay? So maybe what I'm going to do is I'm going to erase this, rewrite this down, and then I'm going to show you what backward Euler is. So just one second. Okay, so I erased everything, and I rewrote my forward Euler here, and I changed my notation a little. Just, I want you to get really comfortable with the subscript notation, because this is how all numerical schemes are written. Is I approximated my derivative x dot at time step tk, at time tk, as x at time k plus 1 minus x at time k divided by delta t. And of course that equals, since it's x dot at time tk, that equals f of x at time k. Okay? And so if this is a little confusing, pause the video, write this down, and convince yourself that this is exactly what I wrote down before I erased the board. And that derived this forward Euler scheme that we wrote here. And then similarly, backward Euler essentially uses this exact same derivative, except now I'm using, this is a forward difference approximation of x dot. Now we're going to do a backwards difference approximation of x dot. So I'm actually going to write it the same way. I'm going to write it as, so this is backward Euler. Backward Euler. And backward Euler, I'm going to write it the same way, where I have xk plus 1 minus xk divided by delta t. This is the backwards difference approximation of my derivative. This is approximately equal to my derivative x dot at k plus 1, at time step t k plus 1. So this, at time k, I would use k plus 1 minus k for my forward difference. So at time step tk, I would use tk plus 1 minus tk for my forward difference, because this is a point that is 1 delta t forward of this one. And that same scheme could be the backwards difference approximation at tk plus 1. Okay, so the derivative of x, and I could write this out as, it's literally exit t plus delta t minus x at t, this is tk, divided by delta t. That is approximately the derivative, dx dt evaluated at time t k plus 1. Okay, so this is, and at time tk plus 1, if I do this minus tk, that's a backwards difference derivative. So that's why we call it backward Euler, because it's based on this backwards derivative. And so notice here, the only thing that changed was x dot is now a function of tk plus 1 on the right, which means this is approximately equal to f of x k plus 1. And so that similarly implies that we can now multiply both sides by delta t and add xk, and I get xk plus 1 equals xk plus delta tf of xk plus 1. This is my backward Euler scheme. Okay, I'm going to circle this one just so you remember. This is my forward Euler scheme. And there's something kind of a little weird happening here, that now, remember, I want to be stepping my system forward in time. I want to be able to predict my trajectory x at time k plus 1 just from the information at x at time k, the current point in my trajectory. And here this makes sense. This is called an explicit scheme. This is explicit because xk plus 1 is an explicit expression of xk. So all I have to do is plug in my data now at time k, at the current time that I have, and I get my time step, my next time step information. This is called implicit. Sometimes it's also called implicit Euler. Implicit Euler, because now the thing I'm trying to solve for, xk plus 1, x at my next time step, is on both sides of this equation. So it's kind of an implicit function. This is an implicit function of xk plus 1. And especially if f is a nonlinear function, I have to do some weird thing to invert this f to solve for xk plus 1. It might be very numerically complicated to solve for xk plus 1. And so what we're going to find in the next lecture is that backward Euler actually has way better stability properties. It gives much more faithful, stable predictions of the dynamics, specifically because of this implicit nature here, but it's much, much, much harder to solve for than forward Euler. So just the fact that I can kind of build this map f, this explicit map f that takes x at time k and spits out x at time k plus 1, that makes this way, way easier to code up and to solve. This one, because it's implicit, because solving for xk plus 1 means I have to invert this function, which might be very, very nasty. This is very hard to solve, but it's going to have better error properties and better stability properties. So we'll come up with that in a little bit. What I do want to point out is the way that we're going to analyze stability and error for these two integrators is we're going to look at the idealized case that we had linear dynamics. So if x dot equals ax, if my dynamics f of x were just linear equals ax, then this would become xk plus 1 equals xk plus delta t times an A matrix times xk. And I could write this as the identity matrix plus delta t times my A matrix times xk. And so, what we're going to do is we're going to look at this idealized case of linear dynamics, and we're going to analyze the error and stability properties of this operator here and see how close is this to the true kind of flow operator that flows my system forward in time, and that's how we're going to understand these things. So here, similarly, if x dot equals ax, then again I would have xk plus 1 equals xk plus delta t. Ooh, how do I want to write this? Delta t a delta t xk plus 1, a delta t times xk plus 1. And now what I could do is I could actually move this over, and I could write this as identity minus delta ta times xk plus 1 equals xk. And I can solve, so if this was linear dynamics, I can solve this implicit equation by just dividing this matrix over. And I get xk plus 1 equals identity minus delta ta inverse times xk. So this would be, again, I'm going to look at the stability properties and error properties of this approximation for implicit Euler and this approximation for explicit Euler, assuming linear dynamics. That's how we're going to do error analysis and stability analysis for these two schemes. And I want to point out, actually, this is super interesting. If you look at identity plus delta ta, these are the first two terms in the Taylor series. So these are the first two terms in the Taylor series for, you guessed it, of x of t equals e to the matrix a t times x naught. So this matrix exponential e to the at, these are the first two terms in the Taylor series, actually specifically of e to the a delta t. X k plus 1 equals e to the a delta t times xk. The exact solution here, this is the first two terms in the Taylor series of e to the a delta t. So you can see already that this is going to be, a first order Taylor series approximation. I can make this error smaller by making delta t smaller, but I might be able to do better by including more terms in my Taylor series. Similarly, this is the first leading Taylor series of, a more complicated implicit version of this. Okay, good. So we know now how to derive these. We're going to use finite difference derivatives. We're going to get these expressions that work for generic nonlinear functions f, but we're going to analyze their error and stability by assuming linear dynamics and then comparing with our exact solution that we know the answer to. We're going to compare these expressions and see if they're stable, what the error is. Good. Maybe what I'll do right now is I think I'm going to stop here, and in the next lecture what I'm going to do is I'm actually going to code this up, both of these schemes, for this spring mass damper system. So I'm going to stop here, and in the next lecture I'm going to derive these equations of motion, and we're going to try these integrators. All right, stay tuned. Thank you.